In a previous video, we talked about how to construct a confidence interval for the differences of two population means based on two independent samples. In this video, we're going to complement that former experience with how to conduct hypothesis testing for the differences of two population means from independent samples. We consider the first example here, which talks about two versions of a course exam. An instructor decided to run two slight variations of the same exam. Prior to passing out the exams, she shuffled the exams together to ensure each student received a random version. Summary statistics of how students performed on these two exams are shown in the table below. Anticipating complaints from students who took version B, she would like to evaluate whether the difference observed in the groups is so large that it provides convincing evidence that version B was more difficult than version A. How would we help use this summary data or summary statistics to test the hypothesis here? The first step would be to let mu of A be the average score on version A of the exam, and mu of B be the average score on version B of the exam, which means that for our null hypothesis, we would of course say that they are no different from each other, which means that the average score on version A is the same as the average score on version B. And that would be against that one of them is more difficult than the other. Okay, and to evaluate the hypotheses above, to test them one against the other using the t distribution, we need to check two conditions. One, does it seem reasonable that the scores are independent? Well, if the exams were shuffled before being administered to the experimental units, the students, then we can say that the exams, the treatment, were randomly assigned, and so independence within and between groups is satisfied. Then, do we have any concerns with outliers? In which case, if there are any outliers, then there will be issues with um, assuming normality. To do that, the summary statistics, if we look closely at it, it does not show any crazy values that are extremely far off from one another. So the summary statistics suggest that the data are roughly what? Symmetric about the mean, and the minimum or maximum values does not suggest any outliers of extreme concern. And with that, we are ready to get into the what? Into the mechanics or the main computation. And that requires us to look at the point estimate of the unknown difference. That'll be the difference in the scores, the average scores for those who took version A of the exam and those who took version B of the exam. That will require me looking at the average sample score for version A minus the average sample score for version B in the sample. So that will be 79.4 minus the second value, which is 74.1, the average score for those who took version B of the exams. And this will be equal to 5.3. Okay, and with that sample difference, we can generate other what? Vital what statistics from the two samples using StatCrunch. So I'm going to go to StatCrunch here, and let me pull that up in StatCrunch. And I'm going to go to statistics, go to tstats, two samples with summary statistics. In this case, my sample mean for the first group, that will be 79.4. And the standard deviation is 14, and the sample size is 30. So we have 14 and 30. And then for sample 2, you have 74.1, and the standard deviation is 20. and the sample size is 27. And I'm not going to choose pooled variance. I'm interested in constructing or testing hypotheses for the differences being equal to 0 versus not equal to. I'd like to show the critical value, and my level of significance for this test is 0.01. Please note that if the level of significance is not provided, then we assume 5% by default. But since it is given 0.01, we're going to use it. So you compute, and I would have these values. In particular, the p-value, the probability value, is what I need. So I'm going to pull that right down here, which is 0.2573. Obviously, this is greater than the significance level chosen for this test. So when that happens, we fail to reject the null hypothesis. What does failing to reject the null hypothesis mean? It means that the null hypothesis won the battle, and we do not have sufficient evidence for the research or test hypothesis, which is the alternative hypothesis. So we write that down. This means that the sample data does not provide strong evidence in support of the alternative. In the context of this problem, this means that we can conclude that we do not have sufficient evidence in sample data for the instructor to be convinced enough to conclude on the alternative that one version of the exam was more difficult than the other. What that means ultimately then is that the professor does not need to worry as far as this sample data is concerned, as long as it is random and representative of those populations. Then the instructor does not need to be worried that one version of the exam was more difficult than the other. All right, with that conclusion in mind, let's take another reinforcing example. In this example, we have a data set called NCBERT, which represents a random sample of 150 cases of mothers and their newborns in North Carolina over a year. 4 cases from this data set are represented in the table to the right, and we are particularly interested in 2 variables: weight, this variable, and then smoke. Does the mother smoke or not? The weight variable represents the weights of the newborns, and the smoke variable describes whether or not mother smoked during pregnancy. Our interest or research question is this: we would like to know if there is convincing evidence in this sample data that indicates that newborns from mothers who smoke have a different average baby weight than newborns from mothers who don't smoke. So we identify 2 populations here. That is the population of weights of babies, of newborns born to non-smoking mothers. And we're going to let the average of that for non-smoking, I'm going to put a subscript N, and the average weights of babies born to smoking moms. And as usual, the null hypothesis is the hypothesis claiming that the difference between the 2 weights is nothing, aka they are the same, versus the difference between the 2 weights is not nothing. If it is not nothing, it is something significant. Once the hypotheses have been set up, we check what? The model underlying assumptions, namely independence and normality. For independence, as long as the data comes from a simple random sample, we can reasonably assume that the assumption of independence within and between the groups is satisfied. Then we also talk about normality. For the normality of the distribution of the weights, that would be satisfied if we plot the histogram of the values for the different classes of smokers or weights of babies of the different smoking moms or non-smoking moms. If we plot their histograms and we do not observe any extreme outliers, so the assumption of normality of observations in that case would not be unreasonable. And that appears to be the case in these two cases. We don't see any extreme values above or below for the separate distribution represented by the histograms. Okay, then with that said, we get into the mechanics or the computation part. Well, what is the point estimate of the population differences? That will be going to the sample. What is the average for non-smoking moms? What's the average weight of babies born to non-smoking moms? That was 7.18 minus 6.78. It doesn't matter which one goes first, whether smoking before non-smoking. I have chosen non-smoking before what smoking, just based on arbitrary selection. And that would give us 0.4. That 0.4 could also have been computed using StatCrunch. So let's go to StatCrunch to get all the vital statistics from the data set. And I'm going to close out of this. And I'm going to go back to the table, the summary table. For each of the groups, for the smoking moms, we are going to need the mean, the standard deviation, and the sample size for each of the sample data values. So we go to statistics, go to t-stats, to sample, with summary, and I'll key in, I want non-smoker first, just my own choice, 7.18, and then sample standard deviation is 1.60, and the sample size is 100, and then for the other sample mean, we have 6.78, 1.43, and then 50. And we want to test the hypothesis that what? The difference is 0 or not equal to 0. So that is already set. And I would like this to be done at a significance level of 0.01. So I have that piece to adjust here and compute. And I have the values here without pooled what? Variances. That's an error there. Oh, I have with pooled variances here. Sorry. You want this to be without pooled variances. So I'm going to edit that here. So this should be without pooled variances. Apologies for that. So I want the critical value of 2.621903. And then we want p-value of 0.1238. And the standard error here should be 0.2578 7206. The degree of freedom is 108,50046. The test statistic value is 1.5511568. So this must be without pooled variances. And the p-value we have here is 0.1238, which is obviously greater than alpha, the level of significance of the test. So, which leads us to fail to reject or do not reject the null hypothesis. And if we're not rejecting the null hypothesis, it means going back to the beginning. The null hypothesis, we are not rejecting it. That means we do not have sufficient evidence again for the alternative. So that means that we do not have sufficient evidence. We do not have sufficient evidence in favor of the alternative hypothesis. And then in conclusion, we do not have strong enough evidence in the sample data to conclude on the alternative. That is, there is a difference in average birth weight for newborns from smoking and non-smoking mothers. So with that, we come to the conclusion of that unit.